Hello friends, in this lecture we are going to learn about circuit switching network and packet switching network. Okay, so this is a very common question that is asked in many interviews. So what is circuit switched network and what is packet switched network? So first and foremost, so circuit switched network, so when two people are talking, okay, and when they are communicating, so there is a dedicated path, dedicated resource for the data communication, and it is continuous flow of data. But here in packet switching, the data is now discretized and it is in a form of a chunk known as datagram. So for example, in this circuit switching network, let's say this mobile is talking to this machine, okay? So there is a dedicated path, this router to this one, then to this, then now I come to this one, let's say this one, then this one, this router and this router, okay? So then to this machine. So this path is now dedicated. So all the data will be flowing through this particular path, and all the resources, the link bandwidth, are now dedicated. So the link bandwidth, switch capacity, they are reserved for the call. So there I'm not sharing with anyone this particular link dedicated path. I will not share with anyone. It's just for me, that particular connection. So circuit, like, it's guaranteed performance, but what you need, so to resource, for reserving the resource or the path and the bandwidth, I need to set up the path circuit, okay? Then there will be data transfer, and finally I will tear the path, okay, so that resource can be released or something like that, okay? So call setup is required here. Now, so what we have here is we have network resources, for example bandwidth. Your link will have some bandwidth, and I will give to a particular circuit, okay, a particular telephone call, a fixed piece of that particular bandwidth. So pieces allocated to calls, resource piece idle, and now what happens if we have the resources not being used, okay, then if it is idle, then there is no sharing, okay, so that's not good in fact. So we have some link, okay, so there is a link, 4 people here can connect to this link here. So 4 people are here, there are 3 here, okay. So now how many? So this is A, B, C, D, E, F and G, okay. So how many? These are 4 people here, these 3 people are here. So for example, D can talk to G, D can talk to F, D can talk to E. So these are different circuits, okay. So there will be, if let's say B is talking to E, there will be a dedicated resource from B to E. So here 4 into 3 different calls can be made. So 12 particular communications can happen, okay. So this link capacity will be divided by 12, okay, for all the different communications, okay, so calls. But what will happen now if say B is not talking to E, then that particular resource will be not utilized, okay. So dividing the link bandwidth into pieces, so how can we do that? Bandwidth can be divided using frequency division, okay, so or using time division. So let's try to see that. So first is frequency division. So we have a whole bunch of frequency here, and there are 4 users. So now what happens? I will divide this whole frequency itself among the 4 users such that they all have their dedicated, if the frequency size is R, I have R by 4 dedicated to each one of them, okay. So for example, this is the first one, second one, third one and fourth one. So all of them are divided 1 by 4th of the frequency, and it's very fair also. But the thing is, if this is user 1, 2, 3 and 4, if 4 is not using the link, it will remain idle, okay. No one will be using it, so it's unutilized, which is not so good. But it's dedicated, and whenever he's using it, he will get perfect quality of service, quality of call. So that's the thing. So this is based on frequency. Now I can also do the same thing. The frequency is here, but I can, instead of dividing the frequency, I can give them time slots, okay, a TDM, time division multiplexing. So now what happens is that the first user will be always, the time will be divided into 4 slots and it will be repeating. So let's say 4-second slots are there for all 4 and 1 second for each one of them. So first second will be blue user, second will be green, third will be yellow, fourth will be pink, and then again blue will start. So this way also, now if blue has data to send during this time period, he will send. But if at this time period he does not have data to send, it will again be unutilized. But here also your time slot is fixed, you have dedicated resources, so it is good in that sense. So let's work out a numerical so that our concept can become clear. How long does it take to send a file of size 64 into 10 to the power of 4 bits from host A to host B over a circuit switched network? Okay, all links are this. All links have bandwidth of 1.536 Mbps. Okay, so I have 64 into 10 to the power of 4 bits, or it is 0.64 megabit. So this is my bandwidth. Okay, then the link, so no, this is not the bandwidth, this is the data size. Okay, so this is the size of the file I have to send. My link speed is 1.536 megabits per second. That is at what rate I can send data. But the thing is, it's a TDM with 24 slots per second. So now it is a TDM, which means there are 24 slots in 1 second. So there will be 24 users, okay, and they will be sharing those time slots. So in 1 second, one user will have 1/24 of the slot. So his effective bandwidth will be 1.536 Mbps by 24 megabits per second in reality. Now he has data is 0.64 MB. So data divided by the rate will be the time taken to send the bits, plus it's a circuit switched network, so you need to set up the circuit, which takes 500 milliseconds. So the time is, now it is 0.64 MB megabits by 1.536 megabits per second divided by 24, so it comes up, and if you do this calculation, it comes out to be 10 seconds. Okay, plus you take 500 millisecond or 0.5 seconds for call setup, so total 10.5 seconds will be taken for delivering this data. Okay, now what is packet switching? So here we saw that, okay, there was dedicated bandwidth. You could use either divide the frequency or time division multiplexing, but here each end data stream is divided into packets. So now I'm not sending the continuous data, I'm dividing it into chunks called packets. Okay, and these are discrete small packets are there. User A, B packets share network resources. So now if there is a link, okay, and here you have A, here you have B, they have data to send here to C. So let's say he has 100 MB of data and this person has 200 MB of data. Now let's say they have to discretize it, means make packet small size. Let's say the packet size is 1 megabit. So now this data will need 100 packets. A will have 100 packets, B will have 200 packets. So now they are sharing this medium. Okay, so there will be a queue here, and they will be sending this data. The packets will be now enqueued in this particular queue, and then it will be sent through the medium. Each packet uses full link of the bandwidth, and each packet will be using the full link capacity bandwidth, resources used as needed. Okay, so now it will not happen that, okay, if A has no data to send and B has data to send, he will use the complete bandwidth. So in this sense it's better, because now nothing is getting unused. If you have data, you can send it. So this is good thing about it, but nothing comes without any cons. So this is the pros. The con is resource contentions. If both of them have data to send, then you will have contention. Both of them will fight for this link. So aggregate, and might happen that aggregate resource demand can exceed the capacity, and there might be congestion. Lot of packets, both are sending packet because no one is stopping them. So the queue might become full, there might be congestion. And one more important thing is it uses store and forward. Okay, so we will look at the meaning of this one. So first is statistical multiplexing. So A and B have data to send. Link capacity is 1.5 megabits per second. So there is a queue here, and they will be sending their packet, and they will be statistically multiplexed, which means that if they have data, they will be getting enqueued here and being sent. So now if let's say, so A and B packet does not have fixed pattern, so it will not happen that, okay, this will allow one packet of A, then it will allow one packet of B, then it will again allow one packet of A, then one packet of B. There will be no fixed pattern. In whatever way they are coming into the queue, it will be sent like that. Okay, so and it was in TDM, they would have been getting slots. Okay, first second A will send, second B will send, but here there is no such thing. Whoever is sending their packets, they will be queued. So store and forward, as I said. Okay, what is store and forward? So let's say there is a computer here, two routers are there. Now L is the size of data that needs to be sent, and R is your rate at which, or link bandwidth, or rate of packet sending. So L by R will be the time required to send this particular packet. Let's assume no propagation delay or zero propagation delay, then it will come here, and only when this router, okay, when it has received all the bits of this packet, so it will store it, then only it will start forwarding. So how much time it has to wait? So the whole packet will take L by R seconds to get stored here, because that is the time it will take to from the first bit to the last bit to reach here. Then when it is done, so L by R time is taken. This router will now start forwarding, and it will wait here for L by R amount. So it will receive the complete packet, store it, then forward it to this one. So L by R is now utilized by this router. Again it will send it here, and this will take again L by R. So it becomes 3L by R. So that was the store and forward. So for example, if 7.5 megabits of size was the packet and rate was 1.5 Mbps, then 7.5 by 1.5, which is 5 seconds, would have been taken for transmitting from one hop to the next hop. There are 3 hops, so it would have been 15 seconds. So packet switching versus circuit switching. So packet switching allows more users to use the network. Okay, it allows more users to use. Why? Because now many users are there, and by law of average probability, not all of them will be using the link. So this is the most important thing. So there is a 1 Mbps link. Now let's say each user uses 100 KB per second, okay, when they are active. But we also have one more point, that they are active only 10% of the time. So what happens if we were allocating dedicated resource, then 1 MB is 1000 KB per second, 1 Mbps. So now one user required 100 kbps, so only 10 users would have divided by 10, so this link could have been used by only 10 persons. But the thing is, we also see that okay, you are not active or you are not using the resource all the time. So it tells that on an average only 10% of the time we are active. Then it says bingo. So now what it says, circuit switching, we would have just got 10 users, but here let's say they have 35 users. So what is the probability, now it is asking that what is the probability that more than 10 users are active at once? Okay, so let's try to see. So 35 users are there and the probability of being active is 10% or 0.1. Probability of being non-active is 0.9. So what is the probability that 10 users will be active? So it will be 35 choose 10 and 0.1 to the power of 10 and 0.9 to the power of 25. And what is the probability that more than 10 active users are there? So if there are 11 active users, 35c 11.1 to the power of 11, 0.9 to the power of 24, and you go on till 35, all the users are active, so 0.1 to the power of 35. So if you sum this up, it will just come out to be 0.0004, which is 0.04% is the probability that more than 10 users will be active. Okay, so it's very less probability. Then we are sure that if less than 10 people will be active, is the probability is then how much? 1 minus 0.0004. So it will be very much more than 99% of the time less than 10 users are active. So they will get their 100 kbps per second speed, and you as a internet provider, you will be happy that all 35 users are paying you the money and you are giving them also good enough service. If you were using circuit switched network, 10 users, you would have got very less money and the quality of service would have been almost the same. So great. How, when is packet switching best? So there is bursty trap data, you don't know when it is going to come. Resource sharing is there, no call setup is required, and it's simpler, but it might have excessive congestion. Let's say if somehow 35 users gets active, then there will be delay, there will be loss, and there will be big problem. How to provide? Then the next questions come is how can we provide circuit like behavior in packet switching, which we will see in next class. So I hope you understand this. Thanks a lot. If you like this video, please subscribe to my channel.